Okay, hello everyone. Today our topic is about electromagnetic induction. Okay, so let's move into the first part, and it's called induced electromotive force and current in a moving wire. Okay, so last time we have discussed that if we have like a magnetic field and we have a current, and based on the left-hand rule, we have a force direction, right? We have a force acting on a wire, right? So today we have a magnetic field. You can find here we have a north pole and a south pole, right? And if you're using your hand to moving the wire downward, okay. So maybe here your hand afford a force, right? So based on the left-hand rule, force, oh sorry, the first finger thumb means force, right? And first finger means magnetic field, and the second finger means the electric current direction, right? So here we have the force direction, we have the magnetic field direction, and they're perpendicular to each other. And we can also have a current direction that is also perpendicular to the magnetic field and with like the current. Okay. So this is for the induced EMF. Like here, you can use this to induct or induce electromotive force. Okay. So like in the second figure, you can find here, okay. And if you're using more wires, and you can find it can afford a more or stronger like current in here, okay. So we can say, oh, maybe here using the hand to move the wire can also afford a current, okay. So you can set here, if you have electromotive force or like electric stronger current inside the like wire. Okay, so here are three methods. Like first, you can moving the wire faster. Okay, so moving faster means you have a stronger force, and there's a more stronger like a force like appeared in the electromagnetic waves. Okay, so here you can say, oh, maybe here you can have a stronger force, stronger current, and stronger for magnetic field. Okay. And then you can use a stronger magnets. Okay, so you just like using the left-hand rule. If one item is very big, that means another item must be very big. They are directly proportional. Okay, so you can say using a stronger magnet. Okay. So last time or the last method, you can increasing the length of a wire in the magnetic field. Okay, so here's the example. Like if you're looping the wires through the field several times, like here, you can increase the current. Okay. And to remember that here, when you're inducing the electromotive force, that always followed with Faraday's laws. Okay. And maybe we will introduce Faraday's law in the next part. Okay. So like you can using this principle to form like this experiment. Like you're holding up a magnet and you're just closing to your coil. Okay. And once you closing to the coil, you'll find, oh, maybe here the pin just starts to rotate like this way. Okay. So why does it rotate? Okay. Like we have like a force, right? We have a force and we have a magnetic field, right? We have force and the magnetic field. That means we have a current in the wire. Okay. They like this way. Okay. So we have current inducing this. Okay. Just based on the three part are perpendicular to each other. Force, current or electric field, and for magnetic field. Okay. They are perpendicular to each other. Okay, so here it is. Okay, and you can find in the second figure, we have a north pole and south pole, we have a magnet, and also you can find it just moving backwards, and you can find current direction also change or also reverse. Okay, so it's the same meaning that you're perpendicular to each other and your direction is also perpendicular to each other. Okay, so this is for induced electromotive force. Okay. So I guess this problem is just like you fell in love with a girl, and maybe you're just maybe she's your crush, okay, and now you're just dating with her, okay. Maybe you're very nervous and you're very anxious about this. And when you're closing to her, and she's also very nervous and anxious, okay. So maybe, oh, she will refuse you. Okay, so please don't close me so little. Okay, so she will push you away, right? So like here, if you're putting a magnet, you will find maybe here it has a current right here, and the current using the right hand grip rule we said before, right? So we have a magnet or like a induced current, and the induced current induce a magnetic field. Okay, so it induces a magnetic field, and on the left is north pole, and on the south is south pole, right? So you can find, oh, maybe on the left north pole, and you will have a like a force like toward the lab. Okay, it will to repulse the magnet. Okay, and on the right, you can also find maybe here the magnets come when it moves away, and you can find the direction of the current just change into another direction. And here is south pole, and here is north pole. Okay, so you can find like you are dating with a girl, and you said, oh, maybe my time is very hurry. Okay, I have to go. So maybe your girl is very anxious, and she said, oh, maybe please stay with me for a longer time. Okay, like this way. So here you can say, oh, maybe here it has a attractive force on the North Pole, or you can find on the magnets. Okay, so it's just okay. So just stay with me for a longer time. It has force. It has induced a magnetic field attract the magnets on the left. Okay. So this is how we can set this phenomenon to explain. Okay, so each time when you're closing, and I will induce a magnetic field to repulse you. Okay, and if you're like come closing to me, repulsive force, and you are leaving to me, I will attract you. Okay, so this is like the induced electromotive force and the moving wire. Okay, so this is for this. Okay, so here you can find, we can set this phenomenon called Lenz law. Okay, Lenz law. So for Lenz law, we can set, oh, right here, and if you're using magnets come close into the north and the south, and you'll find there is induced current. And here is also induced current when you're moving backward to the coil. Okay, this is Lenz law. Okay, so here, what is the Fleming's rule? Okay, so maybe I will say you maybe are confusing about Fleming's right-hand rule because you're back with right-hand rule. Okay, so for this one, you can also using the left-hand rule to remember this. Please remember that the force, magnetic field, and current. Okay, so right here you can say, oh, maybe you have a motion upward, right? That is because the force applied a action toward. Okay, so maybe magnetic field will have a resistive force backwards, right? So it's like when you are coming closer, the coil will refuse you, and when you're coming away, and you'll find the magnets will pull you, right? Give a attractive force. Okay, so right here, if you're moving away from the magnets, and it will also give you a force downward. Okay, so right here we can say, oh, maybe right here, downward resistive force. This means the force applied from the magnetic field. Okay, so you can say, oh, maybe here using your left hand. So upward is a moving direction or the force direction. Okay, so right here you can find, oh, maybe here is downward. Okay, downward. Okay, and second is the magnetic direction. Okay, so magnetic field direction is from the north pole to the south pole. Okay, so it's like this way. N to S, okay. And then you can find your current direction is like maybe toward your body, okay. So you can say, oh, maybe current is from the inner part to the outer part, okay, like this way. So we can say this is a kind of Fleming's right-hand rule, okay. But we can also use in the left-hand rule to explain this, okay? So if you're very familiar with Fleming's right-hand rule, you can just like raise up your right hand and using your three fingers. Okay, so maybe your thumb means the motion, okay? Your first finger means the like magnetic field, and your second finger means the current, okay? So it's like you inversely with the left-hand rule, okay? So which one you choose, just depending on like which you are familiar with, okay? Okay, so here is an exercise. Please just try to, so this exercise, please, okay. Okay, so let's try to solve the problem together, okay. So the question is, a magnet is suspended from a spring so that it can move freely inside a stationary coil. Okay, so here's the coil. Okay, and the coil is connected to a sensitive central like ammeter. Okay, so here is just what does ammeter show. Like here we have A to D, and A is a constantly changing reading, and B is a steady reading to the left. Okay, C is right, and D is reading the zero. Okay. So right here you can find, oh, maybe right here you can find the spring just have a elastic force on it, right? So maybe it will moving downward and moving upward, okay? Like upward, downward, like this swinging in the center, okay? So we can say, oh, maybe sometimes you're moving closer to me, right? So based on the Fleming's rule or based on the Lenz rule, we can say, oh, if you're coming close to me, it's just like dating with another girl. Like I have to refuse you, right? If you're come closer or come further with me, so I'm said, oh, you're very further away, so please stay with me for a longer time, right? So here you have another kind of force. So we have changing current and changing force. So we can say, oh, here is a constantly changing reading, right? Sometimes attractive force, like one current direction, maybe on the left, and sometimes another direction is on the right. So we can say we are choosing a constantly changing reading. Okay. Okay, so this is for today's our lesson. We have already reviewed for all parts, and I hope you can just trying to solve the problems by yourself and trying to make a fully understanding on Fleming's rule and maybe on the Lenz rule. Okay, so see you next time. Bye.